Click on record and off we go. This is unit 9. For reasons I explained a while ago. And we start off with a brief look at Springs and Hooke's law, because I mean, springs have a certain amount of significance in their own right. A lot of mechanical devices have springs in them, but the wider significance here is that this serves as a model for many different types of vibrating systems. Okay, once we get to the, just take one of each of those handouts in those 3 piles there.
Has physics 122 starting today?
Today, starting about 1 minute ago, actually.
All right. I will not be taking physics 122.
Okay, here, let me pause this. So we get to the bottom of the page here, and it'll be, and on after that, it's about vibration. And a mass on a spring serves as a model for anything that goes back and forth, whether it's a tree branch swaying back and forth in the wind, or maybe more significantly, the electrons in a wire that's carrying an alternating current. They go shaking back and forth 60 times every second. The thermal motion of the atoms in a solid, or molecules, maybe I should say, each of the molecules in a solid has a certain assigned position, but it doesn't just sit there at rest. It behaves as if it's connected to it by a little spring. And the higher the temperature, the more vigorously it vibrates back and forth. Temperature gets too high, the crystal lattice just shakes apart, and we call that melting the thing. Sound, okay, if I was standing here whistling a steady tone, the air molecules would vibrate back and forth very much like the graphs on the bottom half of the page here. So the reason that a typical physics book has a whole chapter about springs is not just for the sake of the springs themselves, but because they serve as a model for all of these different types of things. So here at the top of the page, we have this little black thing down here on the end of a stick. That's supposed to be somebody's hand. As you maybe heard me say before, there's a reason I was a physics major, not an art major. So you grab hold of the end of the spring, and in the middle picture here, that's the undisturbed length of the spring. Okay, the horizontal dotted line there is where the bottom of the spring would be if you weren't doing anything to disturb it. In the picture on the left, you've stretched the spring downward a distance x. In the picture on the right, you've compressed it upward a distance x. And at least in an idealized spring, the amount of force from the spring, how hard does it push or pull on your hand, that is directly proportional to x. If you stretch it twice as far, it pulls twice as hard. If you stretch it 3 times as far, it pulls 3 times as hard. As for the minus sign in Hooke's law, that's because of the opposite directions. Notice in the picture on the left, the spring pulls up on your hand, and the end of the spring has been moved downward. Likewise, over in the one on the right, the force is down, but the displacement is up. F and X always have opposite directions. And that's why there's a minus sign in there. The proportionality constant between the force and the displacement is typically called the spring constant, and it's represented by the letter K. for, it depends on how hard the spring is to stretch or compress. If you take a ballpoint pen apart and you get one of those little, the kind of pen that clicks, and you take the little spring out of there, the spring constant for one of those little springs is probably somewhere in the single digits. If you want to talk about the springs in a car's suspension, well, that's actually what's coming up in the next example here. And you can see the answer under it is in the, well into the tens of thousands. So and if you talk about the springs in the wheels of railroad cars, that would be even bigger. And so that's what K is all about. This picture over here on the right, by the way, with the mass with the arrow pointing up and down next to it. Yeah, that was supposed to be down here where it says vibration. Sometimes computers sort of have a mind of their own, and they put pictures where they want them instead of where I wanted them. And I didn't notice until I had it all printed up. So if I ever revise this someday, I'll try and fix that. And of course, something else will go wrong. So here's where I pause the recording for a minute, and you work on problem number 1 and see if you can get the 60,000 that it says there. So the minus sign, as I said, is there because if you're keeping track of the directions, when F is positive, X is negative. When X is positive, F is negative. So if you don't want to keep track of all that, and there is no reason to in a question like this, the simplest thing to do is just to slap absolute value signs onto both sides of the equation. So if you don't care about the directions, Hooke's law becomes just F equals KX. K is what the question asks for. And both those things are given in the question. Actually, I suppose if you really wanted to split hairs, this would be delta F and delta X, because the springs are already compressed by the weight of the car. There's already a force and there's already some displacement of the springs. When you get in the car, that's additional force and additional displacement, delta X. That's just splitting hairs though. 600 newtons of force causes 0.01 of a meter of displacement. I converted centimeters to meters, otherwise the spring constant would come out in newtons per centimeter, which I suppose would be okay for certain purposes, but that wasn't what I felt like doing. $60,000. That actually would be the effective spring constant for the entire system of all 4 springs, actually, rather than one individual spring. So back over here to the note packet. Slide another book under it so it sits a little higher. So vibration, or another word that basically means the same thing as oscillation, is when something goes back and forth, such as this is what the picture over here was supposed to go with. You've got a mass hanging on the end of the spring. You pull it down a little bit, you let go, and the spring pulls upward on the mass. But when the mass reaches the equilibrium position, it doesn't just stop there. It's picked up a lot of momentum and kinetic energy, and so it keeps going. It overshoots, compressing the spring in front of it as it goes, until when it finally stops, it's just as far above equilibrium as it was below when you released it. So then it starts back down. But once again, equilibrium is not where it stops. That's just where it stops picking up speed. And as the spring stretches out behind it, it slows it down, and this process repeats over. If you had a truly frictionless environment, it would go back and forth forever. Well, of course, you never have that level of frictionlessness, but it's a good approximation to reality if you watch the thing for just a short period of time under conditions where friction is fairly low. So down here, it says simple harmonic motion. Simple harmonic motion is a particular type of vibration. As it says there, vibration with a Hooke's law restoring force. Hooke's law is an idealization, okay? Don't be distracted by the word law. It's the term that was fashionable at the time. Robert Hooke was a contemporary of Newton's. So we're talking about the late 1600s, and a lot of things got called laws then. Just in contrast, you get to the early 20th century and Einstein publishes the theory of relativity. Well, the theory of relativity has been put to some very stringent tests for over 100 years now and passed every one of them perfectly. It's as established as any kind of established science you can think of, but it's the theory of relativity because it's from the 20th century, and Hooke's law is a law because it's from the 16th century, or no, it'd be the 17th century. Hooke's law describes how things behave as long as you don't go to too many decimal places and you don't stretch the spring too far. But the idealization here is that you have a perfectly linear restoring force. The force is proportional to exactly x to the first power. And with real world vibrating systems, that often isn't true. A simple pendulum, for example, is not a harmonic oscillator, except it is close enough if you keep the amplitude really small. But if you pull a pendulum way off to the side, it's a nonlinear restoring force, which means that when you draw this graph, it's not shaped quite the same way as a sine wave. Okay, if you have a linear restoring force, then when you graph the position as a function of time, you get a sine wave, just like something straight out of a math book. You get a nonlinear restoring force, and the shape of the arches is a little different. Or actually, you can even have more extreme types of things. You could even have, like, for example, what you get with sound waves sometimes is you could get a much more complicated pattern. I mean, something like that is definitely not harmonic motion. Okay. Now, I kind of sketched it really quickly, but the idea, even though it didn't quite come out that way, is you've got this basic pattern that would repeat over and over. This could be somebody humming into a microphone, and this is the pattern you see on an oscilloscope. And but what you have for their voice is this pattern repeats over and over again. It's a type of vibration, it's a type of oscillation, but it's not harmonic because you don't have exactly a sine wave for this graph. So that's what this word harmonic means. The simple in front of it basically means you're talking about the frictionless case. Terminology. The maximum distance from equilibrium. In other words, how far from the center line to either extreme. That's called the amplitude of the vibration. The period is the amount of time for one complete vibration, which could be crest to crest, the way I've labeled it here, or you could just as easily do it trough to trough, or from any point on the pattern to where it starts to repeat again. The frequency, need another book. Frequency tells you the same thing the period does, just the other way around. Instead of how many cycles per second, the period would be how many seconds per cycle. The frequency is how many cycles per second. Well, seconds per cycle, cycles per second. By definition, these things are reciprocals of each other. T equals 1 over F, F equals 1 over T. And that's rather badly out of focus at the moment. Well, for those of you watching at home, it would be a good idea if you had a copy of this handout printed out next to you while you're watching this, because that would be focused better than this is right now. Let's see if I can fix that. Oh, that fixed it. Okay. So F equals 1 over T, T equals 1 over F. Frequency, as I mentioned a moment ago, is measured in cycles per second. This is given a name of its own. It's called a hertz after Heinrich Hertz, who discovered radio waves about 150 years ago. A little bit of practice with these definitions that I just introduced. You've got a graph down here showing, I probably should have labeled the axes. My 9th grade algebra teacher would yell at me. But this was supposed to be position as a function of time, just like the graph that's further up the page. So based on what's labeled on that graph, determine these things here. So a couple of booby traps were laid for you in this example here. First of all, for the amplitude, I labeled that 4 centimeters on there. The amplitude is not the distance from peak to valley. The amplitude is the center line to either extreme. So the amplitude is 2 centimeters. Center line to either extreme, maximum displacement from equilibrium. I did the same thing to you with the period. A similar kind of thing. The 1/10 of a second that's labeled there, that's just half of a period, okay? 0.2 of a second. Because one complete cycle looks like this. One complete cycle, one complete vibration is the top half and the bottom half of the graph. And this was 0.1 of a second labeled from there to there. If half of it's 0.1, that makes the whole period 0.2. And then finally, frequency. I didn't actually write the frequency down on here, did I? Well, the frequency is 1 over the period. That would be 1 over 0.2 is 5 hertz. So here we are on top of the next page. The frequency of a harmonic oscillator. How many times per second does it vibrate? Depends on two things. First of all, it depends on K, the spring constant from Hooke's law. The stiffer the spring, the harder it pulls. The harder it pulls, the faster the mass moves, giving you a higher frequency when you have a stiffer spring. The other factor is the amount of mass that's hanging on the end of the spring. Mass equals inertia. If something is more massive, it will behave more sluggishly, which slows down its motion and would give you a longer period, a lower frequency. If you go through the details, it happens there's a square root involved. This symbol is the Greek letter omega, which if you took physics 121, we've already encountered as the symbol for angular velocity. We're sort of starting to recycle our Greek letters at this point, I guess, although actually there is a connection here, but won't get into that. Omega equals 2 pi f, where f is the frequency, like you calculated a few moments ago in that last example. Basically, the thing going on here with f and omega, I know it looks like a W, but it's actually an omega. The thing that's going on here is this is, I'm pretty sure, the only place in the whole textbook where you use different symbols for something based on what unit it's measured in, okay? If you want to talk about how tall somebody is, H for height, probably. It's H if you use inches, it's H if you use centimeters. You know, if your velocity is V, if it's in meters per second or if it's in feet per second. But for some reason, on this particular occasion, they use F for the frequency if it's in cycles per second, and they use omega for the frequency if it's in radians per second. 2 pi radians per cycle, omega equals 2 pi times F. So quite often we talk about omega rather than F because it simplifies the formula. You don't have to deal with the factor of 2 pi. The same reason we used radians for a number of relationships in physics 121 for, you know, rotational kinetic energy and things like that. The formula is just simpler if you work in radians. So the frequency in radians per second is square root of K over M. Okay, so that's a few words about vibration, which somehow in physics 131, I managed to spend an entire week on that. But in this course, yeah, we keep it down to about 20 minutes or a half hour. And we're going to move on to waves. So first of all, what does the word mean? A wave is a moving disturbance. If I had a long line of dominoes going across the desk here, and you did the thing where you knock over the first one, which knocks over the second one, which knocks over the third one, and you've got that disturbance propagating along the line of dominoes. That is exactly what the type of thing that this definition is talking about. In fact, that's not terribly different than how sound propagates. If I smack my hands together. The air molecules between my hands are violently pushed outward, and they run into the next air molecules, which run into the next air molecules, just like one domino hitting the next. And the disturbance propagates across the room until it bumps into your eardrum and makes your eardrum move. Movement of your eardrum is interpreted by your brain. We'll skip over some of the anatomical details and just say movement of your eardrum is interpreted by your brain as sound. And so anyhow, that's what a wave means. A wave carries energy. For example, a really loud sound can rattle the windows. It's capable of doing work, moving something around. It does not carry any mass. Unlike if you throw a ball, okay, the kinetic energy of the ball moves from here to there and carries along a chunk of mass with it. In the case of a wave, you just have energy moving by itself without any associated net movement of material. The medium jiggles around a little as the wave goes by, and after the wave passes, everything is as it was. So a moving disturbance, sound, water waves, and so forth, make some material substance move as they go by, sometimes called mechanical waves in that case. Then on the other hand, there are electromagnetic waves, light, radio waves, ultraviolet, there's a whole electromagnetic spectrum. We'll talk about that a little more a little later in the course, just a few weeks from now. One significant difference is that electromagnetic waves will propagate through a vacuum. So you stand out in the backyard and you look up at night and you can see the stars. Once you get past a couple miles worth of air, it's pretty much a lot of nothing between here and there. Whereas sound, for example, will not travel through a vacuum. If we were holding this class on the moon, you're sitting there in your spacesuits, if I had two garbage can lids and started banging them together half an inch from your ear, you wouldn't hear anything. You could see me doing it, but without any air or some other medium to carry the vibration from the garbage can lids to your ear, nothing's going to disturb your eardrum. So electric and magnetic fields change strength. Basically, I'll talk about this a little more at a later point, but basically you have an electric field that gets stronger and stronger in one direction and weaker back to zero, and then stronger and stronger in the other direction and weaker back to zero. And as the electric field is going back and forth like that, there's a magnetic field perpendicular to it doing the same thing. And that's what vibrates back and forth, the way the surface of the water vibrates as a water wave goes by. Another way of classifying waves is transverse versus longitudinal. Focus. That looks a little better. Transverse waves. The medium vibrates perpendicular to the direction that the wave is propagating, whereas longitudinal waves, the vibration is parallel. So I've got a demonstration here. Right down at floor level. Get over here where I can see the monitor. Okay, so we have a long slinky going across the floor of the room here. Give us a transverse wave, first of all. Thank you. If you watch one particular coil on the slinky, it moves back and forth this way across the slinky. For contrast, show me a longitudinal wave now. Right, thank you. If you watch one particular coil on the slinky, it goes back and forth this way now. He's pushing it toward me and then pulling away and pushing it toward me and pulling away. And sound is like this, for example. The air molecules get squished together and pulled apart and squished together. Yeah, you can take a break, thank you. Okay. And of course, the focus is messed up again. That's pretty good. So examples of transverse waves. Light is a transverse wave. The electric and magnetic fields vibrate perpendicular to the direction that the wave is traveling. Waves on strings, such as on musical instruments, for example. If you pluck a guitar string or strike a piano string, it creates transverse waves on that string. Water waves, I said sort of. Water waves are actually pretty complicated. We like to talk about them in introductory courses because you can see them, you know, it's kind of nice from that point of view. You can't watch sound go across the room, but really, if you start getting into it, sound behaves in a much simpler way than water waves do. What actually is going on as a water wave passes, if you could watch one little particle of water, or maybe, you know, like if there's a little tiny chunk of seaweed floating around in the water and you could watch it as the wave goes by, it actually traces out an ellipse, kind of like that. So water waves have both transverse and longitudinal components. But to a casual observer, anyhow, if you're just sitting there on the beach building your sandcastle and you look over at the waves, it kind of looks like it's making the water go up and down, which would be transverse. And so as a sort of a crude first approximation, somebody's not observing very carefully, the water waves would be kind of sort of transverse waves. Longitudinal waves, any sort of a compression wave like sound. When there's an earthquake, it produces both transverse and longitudinal waves, and they're called S waves and P waves, and I can't remember which one is which because I'm not a geologist, so I guess I shouldn't have to apologize for that. But one of them will travel through liquids and the other one is a solids only kind of thing. And that's one of the factors they use to map out the interior structure of the Earth. The Earth's core is a liquid. So the one kind of seismic waves will go through it and the other ones won't. And they can get pretty good idea of the size of the Earth's core and so on from that sort of thing. But anyhow, transverse and longitudinal waves. Well, I drew another graph. And maybe a little higher still. Displacement of the medium on the vertical axis, your position in the medium this time. The graph on the previous page had time on the horizontal axis. Actually, I have another copy of it right here. So this was page 32. How much the medium is displaced as time goes by. From there to there was the period. Now I've called it the wavelength instead. The period and the wavelength are two different things. You don't want to confuse them with each other, even though they look like the same thing on the graph. The difference is this graph is as if you went to the beach and took a photograph of the water. You have frozen an instant in time, and lambda, the wavelength, Greek letter lambda, is the distance from what, well, it's what its name says it is, wavelength. It's the length of one wave in the whole series of waves that's approaching the beach. Okay, so the wavelength would be measured in meters or feet if you're old school. And time, on the other hand, the period is time. That would be measured in seconds. So that's, the period is like if you've waded out into the water and you've got a stopwatch with you. And just as the water is topping out under your chin here, you start the clock, and then the water goes down, and then the water comes back up. And when it gets to your chin again, you stop the clock. That much time is the period. The length, the distance from one wave to the next, that's the wavelength. As for other terminology, amplitude, frequency, period, that all carries over from what I said about vibration. The medium vibrates as the wave goes by. And so all of the terminology for talking about vibration applies if it's a periodic wave. I mean, you can have just a single pulse, you know, if I stand here humming a tone, a note, for a sustained amount of time, the air vibrates back and forth over and over and over again. But if somebody just pops a balloon, you just get a sudden pulse of sound that's not really a periodic repeating thing. But if the wave does cause a repeated vibration, then all of that terminology, the frequency and so forth, carries over. If you're talking about sound, amplitude is the loudness, and frequency would be the pitch. If you go along a piano keyboard and you hit a low note, and then as you're walking along, you hit a higher note, and then you get to the other end of the piano and you hit a really high note, that's increasing frequency. The air vibrates more rapidly for the high notes. So frequency is the pitch, amplitude is the loudness. If you're talking about light, amplitude is the brightness of the light, and frequency would be color, meaning the colors of the rainbow. You get a color like brown, and that's a mixture of different frequencies, but the, you know, red, orange, green, blue, that sort of thing, those are light waves of different frequencies. And then one more thing on the list. The speed of the wave. We're talking about the speed of sound, the speed of light, or, you know, how fast a water wave travels across the lake. The primary thing that affects the speed of a wave is the medium. Okay, we're going to do 2 different labs in the next week or so, week, 2 weeks maybe. 2 different labs that measure the speed of sound. For one of them, you use a frequency of around, you know, a few hundred hertz. And for the other one, you use a ultrasound of about 40,000 hertz. Okay. No, he says he's not coming back.
He's not coming back.
Well, not to this class. Yeah, he's not taking the second half.
Oh, okay.
So he's probably gone off to some study hall somewhere or
Okay,
something like that.
Okay, thank you. Sorry to interrupt.
Oh, that's all right. anyhow, in the one lab, the frequency is 2 orders of magnitude higher than it is in the other lab, and you get essentially the same thing for the speed of sound. On the other hand, we aren't going to try and measure this at any point in this course, but the speed of sound in water, like if you're designing a sonar system, is something like 5 or 6 times the speed of sound in air. So it's the medium that, well, you know, in idealized textbook types of problems, the medium determines the speed of the wave, period. Now, if that was true, there would, for example, be no such thing as rainbows. The speed of water waves depends somewhat on the frequency, even though the main factor is the depth of the water. But anyhow, the speed of the wave is what we're talking about right now. And there's a relationship that you'd get a lot of use out of in the little box near the bottom of the page. Where that comes from is the idea that speed equals distance divided by time, which is probably one of the first things I said at the beginning of physics 121. Meters divided by seconds gives you meters per second, or miles divided by hours gives you miles per hour. Well, in a time of 1 period, a wave will move over a distance of 1 wavelength. And so if you fill that into speed equals distance divided by time, that tells you that the speed of the wave equals the wavelength divided by the period, which is a perfectly good equation. But for some reason, it seems people quite often want to talk about the frequency rather than the period. So since F is equal to 1 over T, that because of that, dividing by the period would be the same thing as multiplying by the frequency. And we get, you know, substituting that in, you get the version in the box there, V equals F times lambda. And of course, all this stuff is on your formula sheet, the thing for frequency of a harmonic oscillator at the top of the page, and this thing down here at the bottom of the page. And the speed of sound and the speed of light are on the formula sheet also. I can't remember if I wrote them right next to the formula or if I stuck them in a table further back, but all of that stuff is available to you when you'll need it most, such as during some sort of a test. So, example at the bottom of the page. The wavelength of middle C, and I just wrote in the solution there. If V is equal to F times lambda, it follows from that lambda equals V over F. You divide both sides of the equation by F and solve for the wavelength. Speed of sound, you get off the formula sheet, like I just mentioned a minute ago. And the frequency is given, so you divide 1.31 meters for the wavelength. What that means, once again, is, remember, sound is a longitudinal wave. As sound waves go by, the air gets squashed together and pulled apart and squashed together and pulled apart. 1.3 meters would represent the distance. 1.3 meters is probably about that far. This is the distance from one sheet of compressed air to the next, okay? As the wave goes by, the air pressure goes up and down, just a tiny amount compared to the total atmospheric pressure, but you'd have one region of maximum pressure here and the next one here, and those compressions are moving along at 343 meters per second. At room temperature, you get, it changes by 0.6 of a meter per second for every degree Celsius. But at room temperature, depending on the temperature you keep your room, it's around somewhere between 340 and 345. Anyhow, that's what the wavelength of the sound would represent, the distance from one maximum compression to the next. or one minimum to the next, if you'd rather do it that way. So we're just buzzing right along here. Prepare 2 pages so far. And what's left is, well, it's not the only thing that's left, but what's next is a whole bunch of sample problems for you to work on and get a little practice. I guess I should turn it this way. Why is this suddenly so hard? Yes. Yeah, that looks about right. So 939495. I pause it. You work on those. When you need help or think you're done, you start the recording up again. You know the drill by now.